This is the YQM-98A, and it's, of course, prototype RPV. This is its first flight. The flight controls are being monitored by an onboard mini-digital computer. This computer is capable of being programmed to perform an entire mission profile. The RPV has sufficient redundant systems, both airborne and ground, to assure the mission reliability the program requires. Let's look under the skin. A good place to start is flight control. There is total dual redundancy: control actuators, gyros, sensors, and control electronics. All dual, all with onboard computer programs. Redundancy is equally apparent in the electrical system. DC generators backed up by dual batteries. The AC inverters backed up by an AC generator. The landing gear and brake hydraulics have an independent pneumatic backstop system. In command link, the redundancy becomes quadruple. Two separate MCGS systems, plus dual UHF systems. Any one of these four links can fly an entire mission. The prototypes are powered by a new GARRETT ATF-3 engine, with very low fuel consumption, low noise level, and is relatively smoke-free. But this RPV program started back on the drawing board in June of 1972 with a YQM-98A design effort. 18 months elapsed from award of contract until simultaneous rollout of the two prototypes. Then 3 months of intensive training with computer simulation of vehicle flight dynamics and the interface with MCGS stations, UHF stations, and telemetry vans. There was hands-on training for runway controllers using King Air 90 equipped to receive MCGS and TAILAR data. This provided dynamic landing approach simulations for the alternate semi-automatic and manual landing modes. Here, the controllers make glide path adjustments by means of a bore-sighted television monitor. Such simulations were also run at night. The two RPVs were transported from San Diego in an Air Force C-5A. By the end of April, both the flight test crew and the RPVs were at Edwards Air Force Base. It followed at once a vehicle and support equipment build-up, taxi tests, checkout, and calibration. And on the 17th of August, 1974, the successful touchdown of the YQM-98A first flight. The major flight test objective was this long endurance flight, which will span more than 24 hours. It's 5:30 a.m. on the desert at Edwards Air Force Base. The vehicle and its ground equipment have been pre-funkered. The onboard computer begins its check. Using aircraft power, the mini-computer rapidly checks all primary and backup flight control systems. In just 20 minutes, final verification is received on what could otherwise be a one-day manually performed system check. As the ground stations report a green status, control of the YQM-98 is handed to the primary runway controller. Umbilicals disconnected, chocks pulled. Brakes released, and floorboards advanced. than half a minute, the vehicle is airborne, climbing in its takeoff mode for about 3 minutes. At that point, control is handed from the Untitled Chapter controller to the primary MCGS van, which will retain basic control through the entire cruise mission. However, the entire mission, from takeoff to landing, could be controlled from either a UHF or MCGS control station. Safety chase is provided by a U-2 for the first portion of the mission. The cruise climb section of the mission, to the mission altitude, is routine. Once mission altitude is attained, any additional climb will be the result of fuel burn-off. The primary MCG command and control van records vehicle condition on a continuing basis. Also, the ground track of the flight is recorded on an XY plotboard. A similar record is being acquired at the Edwards Flight Test Center telemetry station, 79 channels of real-time downlink instrumentation data. There is an additional independent telemetry van adjacent to the primary MCG control van, which monitors on continuous reading meters 20 pre-selected flight parameters with instant alarm indicators. 48 channels of real-time brush data are also recorded in this van, as well as all 79 channels on magnetic tape. This provides both on-site quick-look data and permanent detailed records for post-flight evaluation. The routine of a long-endurance flight has set in. 4 hours have already elapsed, and the crews are being changed. This 4-on, 4-off pattern will continue through the day and night. High above the California desert, the YQM-98A flies its prescribed course. It is ready to instantly switch to a redundant mode in the event of an out-of-tolerance condition. Another crew change as the flight continues. All systems still go. The mission has been planned to keep the vehicle within glide distance of the lakebed runway, so that if an engine malfunction occurs, a successful dead-stick landing can be made at the takeoff site. This is the final crew change, and there is an air of excitement starting to build. This crew will land the vehicle. The throttles are reduced to idle. The planned landing sequence has begun. 30 minutes from now, touchdown will occur. The U-2 rejoins for descent and landing. Should a quicker descent be required, landing gears and/or spoilers can be deployed, which will cut the descent time from altitude to a minimum of about 8 minutes. When the RPV arrives at 5,000 feet, landing mode enable is engaged, thus making the vehicle receptive to landing command. The vehicle is directed for a landing approach. Spoilers, now closed loop, are automatically deployed until an altitude of 4,000 feet AGL is reached, and then that altitude is maintained. Then, at the correct predetermined point, the vehicle goes into a nominal 13.5 foot per second rate of descent, a 4-degree glide path. This descent can be adjusted either by the onboard computer or remotely by a ground controller. 3 distinct landing modes are possible. The most automated uses TALAR, Tactical and Landing Approach Radar. If TALAR is invalid, a TALAR inhibit command reverts the flight control system automatically to semi-automatic approach mode. In this mode, the onboard computer uses radar altitudes to maintain the vehicle on the glide slope. Azimuth control is maintained through the automatic heading hold mode. Crab angle for approach is established by remote heading slew commands. The flight control system roll axis maintains wings level. The third system, manual landing mode, can be actuated by the flight control officer, giving him sole control of the lateral and vertical path of the vehicle through the remote control command link. During a TALAR landing, a runway-mounted multi-beam microwave transmitter sends signals to the vehicle as it is on final. 4 bore-sighted beams are received. 2 for azimuth control, 2 for elevation control. The beams are processed by an onboard Taylor receiver, which in turn outputs azimuth and elevation glide path error to COPAR flight control and computer system. A second Taylor transmitter provides for automated lateral steering control during landing and rollout. 70 feet above the ground, the radar altimeter signal automatically initiates flare by commanding a 2-degree nose-up attitude and a 2-foot-per-second rate of descent to touchdown. Taylor is deactivated at flare. 15 feet above the ground, a deep crab maneuver is automatically commanded by the radar altimeter signal to take out any vehicle yaw due to crosswind. Touchdown occurs with the vehicle nearly aligned with the runway. Control system logic commands the elevators full down to press the nose, and fully extends the spoilers to increase drag and decrease lift. The second Taylor, located at the end of the runway, provides azimuth-only steering command. At approximately 75 knots, the brakes are manually applied. The rollout completed, and the engine shuts down. The outstanding success of this high-altitude, long-endurance flight completed the major objectives of the flight test program. Thus, the frontiers of aviation technology have been rolled back a bit further by this Air Force RPV program.